So last time we talked about the minimal sufficiency of likelihood ratio or likelihood process, if you want, likelihood ratio process. And we saw that there are different ways of writing it. Basically, there's this unique up to bijection minimal sufficient statistic, which is the likelihood ratio of the model, or you can think of it as the likelihood function up to multiple factors. So the shape of the likelihood up to a scale factor. So if I plot the likelihood function, and if I ignore multiplication by a factor, that would be minimal sufficient. So the idea is that if there's a statistic that allows me to recover either the likelihood ratio process or this likelihood function up to a constant, multiplicative constant, then like there's a bijection between that function and my statistic, then I should be able to conclude that the T is minimal sufficient. And we did sort of an example where we look at the Gaussian family, and in Gaussian family, the likelihood, like Gaussian location family, the likelihood was like this, up to a multiplicative factor, or the log likelihood is like this, up to a constant shift. And this is in bijection to the sum. And so the sum is minimal sufficient. So if I give you this shape, you can recover the sum by differentiating. And if you give me the sum, I can recover this shape up to a shift. And so that's the rough idea. And for the Laplace vacation family, we did the calculation, and it sort of, this function is minimal sufficient, and this function itself, which is just the log of this, is in bijection to the order statistic. So if I have the order statistic, I can reconstruct this shape up to a shift. And if I give you this shape, you can reconstruct the order statistic, but you can't recover, for example, individual data points because of the sum. So the sum, so we get rid of the order. And so there's a natural redundancy here, which is the order, which is obviously gone. But beyond that, the idea is that the likelihood of this model, the likelihood up to a, or the log likelihood up to a constant shift is proportional, is in one-to-one is in one-to-one correspondence to these order statistics. So the order statistics are minimal sufficient. So if you think about this, or like read about this a little more and contemplate what we did, this should sort of become clear what we're talking about. So roughly that the likelihood function as a function is minimal sufficient. I'm going to come back to this. So this is the case where we have no common support. Usually have a discussion about empirical distribution and this being minimal sufficient in a certain family. I'll let you read about this yourself or look at the slides. Just want to give you two formal theorems. So we saw one from Keener, sort of, and these are formal statements from theory of point estimation by Lehman, which is linked on the website. And so if you really need precise statements, these are examples. So in the VCS family, where you have a finite number of parameters, so the parameter space is finite, this likelihood ratio vector is minimal sufficient. Basically, we have proven this. And then there is this result, which is saying if there is a family, potentially with a parameter space which is uncountable or infinite in a sense, and there's a subfamily, P naught. So this notation means, remember, these are collections of probability distributions indexed by the parameter, right? So you can imagine P is P theta in omega, and then P naught is the same family, but now theta varies in omega naught, where omega naught is a subset of omega. Okay. So the idea is that if there is this subset relation, if the statistic is sufficient for the bigger family and minimal sufficient for the smaller family, then it has to be minimal sufficient for the bigger family. Okay. This is sort of obvious. The only thing that you have to do is worry about almost everywhere P naught implies almost everywhere P. So this is taking care of the thing that we actually ignored, which is that all those statements that I had, that one statistic is a function of the other, is only required to hold almost everywhere with respect to a family. So if a statement holds almost everywhere with respect to this P naught, the way it's defined is this notation. Means that almost everywhere with respect to every P theta in the family. Obviously, it's also almost everywhere with respect to this. That is actually not obvious, but I'll let you think about whether it's obvious or not. But that's the only thing. If S is sufficient for P, then S is going to be sufficient for P naught. This part is obvious. And then P is minimal sufficient for P, then that it can be written as a function of any sufficient statistic in P naught, and so you take any sufficient statistic for P, it's going to be a sufficient statistic for P naught, and then because P is minimal, P can be written as a function of S, almost everywhere P naught, because it's minimal, and then it just replaces with almost everywhere P. So this gives me the second criteria for minimal sufficiency. Just think about this proposition for yourself. It's not difficult, but this gives you a formal way of dealing with infinite families. If you really have to, like someone asks you to write down a precise proof, worried about all the theoretic issues, one idea is to try to pick basically what this is, how this is used. They pick a finite accountable family, subfamily of this. You show that something is minimal sufficient in that, and it's sufficient for the bigger family, so it's sufficient for the whole time. We combine these two propositions, it gives you another way of being precise. You don't necessarily need to do it. I'm just giving you pointers. So here's, for example, a way of doing that analysis that we did for the Gaussian location families. Suppose you have x1 up to xn are normals, mean theta and variance 1. You look at just a subfamily of 2 points. Just take 2 arbitrary theta naught and theta 1, which are different. We know that this is sufficient for the whole family by factorization. And by this proposition 2, because I'm in the subfamily, I just have 2 parameters. This just reduces to just 1 likelihood ratio. So this is minimal sufficient in that 2-point family. And so I'm going to form this. You do the analysis, calculation, and you take the log. The log is in 1-to-1 correspondence. So it's like you have, because log is invertible, like the bijection. So if this is minimal sufficient, then the log is minimal sufficient as well. So we look at the log, and you can see that the log is, so this is a linear function, or like a fine function of t of x, if theta 1 is not equal to theta naught, which we took by design. And so this is in violation to t of x. And so this is saying that t of x is minimal for this family. You also know that t of x is sufficient for the whole family. So t of x is going to be minimal, sufficient for the entire family. This is another way of, clean way of proving that this is minimal sufficient. Okay. You just have to pick the right subfamily, which may not be obvious. So in certain cases, this works fine. The approach is based on just looking at the likelihood are easier in general. But this gives you another formal way of dealing with minimal sufficiency, okay? pick a family, pick a subfamily, show that it's sufficient for the big family, minimal sufficient for the smaller family, and you're done. Okay. So I let you think about these, nothing very fancy here. The thing that I want to discuss is this case, which is of interest. What happens when there is no common support? And here's one example. So you have these three probability distributions, uniform on -1 and 0. So this is the density, expected Lebesgue measure of P naught. And then uniform is 0 to 1. This is the density of that. And then I have this quantity, or this PDF. It's like goes up linearly up to 1. And it has to be, the slope has to be 2 for it to integrate to 1, and just drops other way. So these two have common support, but the support is disjoint with the first one. Okay. So let's say if I naively apply what we learned, so this is a finite family, everything is fine, finite parameter space. So maybe I'll take P naught as my base and form the likelihood ratio as P1 over P naught, P2 over P naught. And you can see that it's like formula is just 0 or infinity. So P1 and P2 are 0 on -1 and infinity. So I get 0 here. And there's something non-zero, but the other P naught is 0 and the 0 to 1. So I get either 0 or infinity. This is fine. This is just saying that this basically both of these coordinates are in one-to-one correspondence with a function that's sort of 0 and jumps to a value. Okay, so if I have a function that takes x and just records basically its sign, whether it's positive or negative. So this is saying this statistic just records the sign of x, throws everything else out. Okay. So this suggests that this is minimal. So it's minimal to just take the sign of x. Okay, forget about the magnitude. But that's not quite true. So x has more information beyond its sign. Anyone can roughly argue why. So if I have the sign, I can tell you, for example, which of these two cases happen. Either this happened or this. So if I observe x, which is positive, I know that this can't have happened. So I can discriminate between P naught and P1, P2. But based on the sign, I can't discriminate between these two. So this naive approach suggests that that's all I can do in this model. Okay? But does the amplitude here carry information? Yeah.
This small yeah.
So small p's are PDFs. Big ones are distributions. So if you want, this P naught of x is indicator x in -1 and 0.
So
the graph is a PDF. So x P naught of x, x P1 of x, x P2 of x. So if I do this naive approach, it's not naive, but I'm basically using this. So pick P naught, P theta naught, let's get P naught, and then divide the other PDFs, P1 of x divided by that, P2 of x divided by that. Both have the same information basically. So this suggests that this is minimal sufficient. But in this case, that DCS assumption fails. And so the question is that, is this enough? So this is basically saying that the sign of x is enough. I don't need the magnitude. I can throw away the magnitude. The magnitude has no information in this statistical model. Is it true or not? Why not? Just intuitively, why? The
difference between
Right, okay, so the magnitude can tell you something about which one has occurred. Not perfectly, but if x is very close to this, it's more likely that this has occurred than this. So if x is closer to 1, it's more likely that this happened. So in this case, what would happen is if I add P2, for example, to P1 or P1 to P2, if I include this ratio as well, then just add it to the mix, then it's going to be minimal sufficient. So this ratio is saying, so you take the ratio as a 2x times that, or you can think of it as just the positive part of x. So the first one is whether x is negative. So you can think of this as in bijection to indicator of x negative. This is okay. Or x positive if you want. So that carries that amount of information. This one is in bijection to positive part of x, which is just this. Equal to x times indicator x positive, that's the positive part. So this thing is minimal sufficient, or you can also note that this can be written as 1 minus x plus. So in the end, if you think about it, x plus is minimal sufficient. So x plus is x times the indicator that x is positive. Or if you want maximum of x and 0. So if it's x is bigger than 0, it's x. If x is less than 0, it's 0. So what this is saying is that if it's x is negative, I'm going to throw away the magnitude. If x is positive, I'm going to keep the magnitude. So that the part that's redundant is the magnitude of x when it's negative. When it's positive, it's informative. And so this part is just, don't worry too much about it. The conclusion matters. So basically like P1 divided by P naught and P2 divided by P naught is not enough. But if I add like P2 over P1, this turns out to be minimum. And there is a whole problem in period point estimation that works through this. You need to add the other ratios, enough of them to be sufficient. But it should give you the intuition, what can go wrong and how you can fix it. Okay. Sounds good. Intuitively, yes. If you want to prove it, you're welcome to try. Right? We're not losing too much. It's just the fact that this is sufficient is should be sort of easy. The fact that it's minimal, it's a good exercise. I think this is actually one of the exercises of here by estimation. So prove that it's minimal for yourself. Okay. It's a little tricky because of all the zeros and stuff, but once you get the intuition, you should be able to prove. Sounds good? Shall we move on from minimal sufficiency? Questions? Yeah.
So then this minimal sufficiency statistic is actually a pair of values.
Yes and no. So minimal sufficiency is like a fluid concept. So it's like anything in bijection to this. So it looks like a pair, but you can also write it as just x plus because this is also a function of x plus. So it's not, yeah, so you can write this as like 1 minus x plus here. In this particular example, if x is it true actually? Maybe this is not correct. But I can write this as a function of this. So if I look at this, if x is positive, then I set it equal to 0. So it's like consider a function of x, which is 1 if x plus is 0, and 0 if x plus is positive. Okay, then this is gonna be 1 if x is negative, and it's gonna be 0 if it's positive. So this is gonna be equal to indicator of x less than 0. So this is suggesting that this is not correct, but indicator of x plus positive, something like that. So it can be written as a function of x plus. So in this particular model, okay? Maybe any time, yeah. Yeah, if x plus is positive, then x has to be positive, so it can't be negative. And if x plus is 0, under this particular model, the only way it can be 0 is if it's, so the thing is, x equals 0 doesn't happen. Under any of these models with probability 0, x equal to 0 happens. It's either positive or negative, so you don't have to worry about the 0. So under this model, you can say this holds. This one holds almost everywhere p. So under any of these probability models, this holds with probability 1. Because we don't have to worry about the case where x is 0. That's where the almost everywhere p helps. Either x plus is positive, which means that x has to be positive. Or x plus is 0, because x equals 0 doesn't happen. It means that x has to be negative. So, seems to be correct. Okay. Yeah.
So confused, how x positive is enough to, differentiate P1 and P2.
It's not enough to differentiate them, but statistically is informative about, right? It's not, so this model does not have enough information to like completely determine which one happened. But the statistics is like the game of just trying something. The best that you can do is better than nothing here, right? So there's going to be a probability of error. So if you just want to decide between these two best based on a single observation, you're not going to do a good job, but it's better than nothing. So you can't throw it away. Okay? So it's more likely. So if you observe x is like 0.95, it's more likely that this happened. This was true than this. Okay, and then you can try to formalize this. Yeah.
If x is positive, then x plus will be positive, and then indicator of that will be 1.
Yeah, 1 minus. Like, okay, or so, okay. Is this gonna work?
Yes.
Yeah. Finally, right.
X plus couldn't be negative. That's what we see. X plus.
Is this correct? Yeah, probably.
1 minus
Yeah, okay. 1 minus this, right? Okay.
1, so
1 minus indicator that x plus is 0. If x plus is it greater than 0? But then it's so if x plus is bigger than 0, x is positive. So then this would be 1, and this would be 0. If x plus is, if x is negative, this is going to be 0, and this is going to be 1. But then this is equal to indicate that x plus is 0. Yeah.
Oh.
Yeah, so these are all seems to be correct. You're right. So I'll let you figure this out. It's not difficult. Yeah, it's just probably making something like this. Okay. Yeah, it's really fun. Yeah.
So you are saying that usually L is minimum sufficient if we write it as of the P. P naught.
No. So L is minimal sufficient if you have a DCS family, let's say. Yes. You have to add that piece, yes. Yeah, so this is the case where this fails. If you have the DCS, then once you add these ratios relative to one of these, then it would be enough. It would be minimal sufficient. But in this case, this fails. And it turns out that now you have to add one more. And in general, more of these pairwise ratios. There's a bit more general result as a like homework problem in tier point estimation. If you're really interested, I can assign as a homework problem. Depends on how much interest usually the class shows. It's a hard problem, but
Proving X1 is sufficient.
proving the more general result when the DCS family fails. Not that you guys seem to be interested in it. I have to assign it as a homework. Right? Bonus, yeah, it's like most of the problems are bonus, yeah. So you don't have to do all the problems. I'm just gonna put it there. You're welcome to try. Okay, sounds good. Any more questions?
I have
Yeah.
a question for the Gaussian location happens built at this time. Then
This one. Right.
yeah. Okay, so based on this, how many P of X is?
Minimal. Because we showed, or you show in the homework problem, that T is sufficient for the whole family, for the bigger family.
Yeah.
And T is minimal for the smaller family.
Yeah.
Okay, so anyone can tell us why T is minimal for the smaller family?
Because T is a function of L, log L.
So this is minimal sufficient.
Yeah.
Right, and so this is minimal sufficient. Why? Because log is 1 to 1. And then this as a function of X is in bijection to T of X.
Oh,
Right. Sounds good.
this is bijective.
Bijective because it's an affine map. So if I give you T of X, that's determined. So it's like saying f of X is equal to A G of X plus B. And then G of X would be f of X minus B over A. So if I have f of X, I can recover G of X. If I have G of X, I can recover f of X. So this is a constant, this is a constant. Theta 0 and theta 1 are 2 points that you pick yourself. Okay. Let's say 0 and 1. Sounds good. Any more questions? Okay, I think we have had enough of minimal sufficiency. So there is something else you can do, which is even better than minimal sufficiency. And so traditional statisticians, the classical statisticians were not happy with minimal sufficiency. You can like squeeze the data more, which in some cases you can. Then let's do that, so compress even more. So what is the idea? The idea is that first you have to understand what ancillarity means, or ancillary statistic. And an ancillary statistic is a statistic, V functional X, whose distribution does not depend on theta. So this sort of, in a sense, intuitively doesn't carry any information about theta. So no matter what p theta you're under, the distribution is like the same. So an ancillary statistic is useless in a sense, the opposite of sufficient. And then there's the first order ancillarity, which is saying the expectation of V does not depend on theta. So if I take the expectation of V, and I have the theta here. So remember, this is a shorthand notation for v of x. So what we're saying is that the expectation assuming x is distributed by p theta. So this is constant as a function of theta. Then we say it's first order ancillary. So based on its expectation, I can determine the theta. Maybe based on higher order moments, I can't. This is a weaker notion of ancillarity. Okay. So an example is something like this. If you look at the location family, any location family, remember these are shifted versions of the same distribution. So x, let's say i's are IID from f of, let's say this is the density, theta in, let's say R, for example. So if I look at the pair, and if I subtract them, the distribution does not depend on theta. Okay, because it's not hard to see that in a location family, you can do something like that. You can write xi's as theta plus some noise, where the noise is just has this distribution, let's say f of x. Okay, by adding theta, you just shift. This is like a simple property of or how things like transform distributions or PDFs transforms under transformation. So if I have a random variable distribution of f of x, if I add theta, the distribution or the PDF of this could be f of x minus theta. So this family can, or like this model can be represented as xi theta plus some noise, which is independent of theta. So xi minus xj, then you can see the theta goes away. So this would be epsilon I minus epsilon j, whose distribution does not depend on theta. Same goes for xi minus the j order statistic, or the I order statistic minus the j order statistic. All of them are theta plus the order statistics of epsilon. So all of these are the mean also would be the same. So mean would be theta plus the mean of epsilon. So this also would be like theta plus the ith order statistic of epsilon minus theta plus the mean of epsilon. So it's going to be something about the epsilons, theta's order. So all of these are ancillary statistic in a location family. So what would be an issue? The issue is we saw in the Laplace family that the order statistic is Laplace location family, that the order statistic is minimal sufficient. Okay, so if I had the Laplace family, x1, x2, up to xn, the order statistic is minimal sufficient, but there exists a function of this guy. For example, the function that takes the first element and subtracts the second element. Let's say x1 minus x2. So let's say f of z1 up to zn is z1 minus z2. Okay, there I can find a function. Then when I apply to the statistic, this is ancillary. I can find functions of my minimal sufficient statistic that are still ancillary. So this suggests that there is some redundant information there. So it's like an intuitive idea, but past statisticians didn't like this. The fact that it's minimal sufficient, but I can form functions of them, non-trivial functions that are still non-informative. What is the opposite? The opposite, the interesting case is a case where we have a minimal sufficient statistic such that no non-trivial function of it is ancillary. whatever you do with it, there is some information about theta. So that's like a condensed ball of information about the model. Okay. So that's the idea of completeness. So completeness is the case where this doesn't happen. So you have a statistic, it's minimal sufficient. And whatever you do with it, except the constant function. So I can have a function that takes this and maps it to a constant. That's obviously ancillary. But if you disregard the trivial functions, the constant functions, any non-trivial function that you apply, the output is not ancillary. So this fails in this case. So we're not in the good case. So let's define the good case. So we want to avoid this. So stronger notion that minimal sufficiency is completeness, and in fact doesn't require minimal sufficiency. It implies minimal sufficiency as a consequence. So we say a statistic is complete if this conditional statement holds. So whenever you take a function of t and take the expectation under theta, so this is really t of x. Implicitly, you're saying x is distributed like t theta. That's all hidden. So I take the expectation, this ends up being constant for all theta. That's the premise. If that happens, then that function has to be constant for all t, or almost all t, as we'll see again. So what this is saying is that the contrapositive basically. So if this doesn't hold, so if the function is not identically constant, then this fails. So if the f of t is not first order ancillary. So this is saying f of t is first order ancillary. So if you want to like state it, if f of t is first order ancillary, then f has to be constant. That's what completeness is saying. Whenever there's a function of t, which is first order ancillary, then it has to be constant. So it's a very strong statement because it obviously includes the cases where f of t is ancillary. If f of t is ancillary, then it has to be constant. Because if something is ancillary, it's first order ancillary. They're saying that even first order ancillarity can't happen for non-trivial functions. Another way of saying it, no non-constant function of f, or the function of the statistic, is first order ancillary. Okay, that's the notion of completeness. So a minimal sufficient statistic need not be complete. Example is this guy. Okay, so we have a minimal sufficient statistic. I can form a non-trivial function of it, which is ancillary. So this can't be complete. And it turns out that this means that the Laplace location family does not have a complete statistic, because we'll show that if a statistic is complete, it has to be minimal sufficient. So if you found a minimal sufficient statistic and you processed it in a non-constant way, it turned out to be ancillary, then it means that this family does not have a complete statistic, or complete sufficient statistic. So the definition of completeness doesn't have anything to do with sufficiency. But a complete sufficient statistic, so if it's complete and sufficient, we'll show that it has to be minimal. Okay, this is completeness. Is this sort of clear? So it's surprising that there are families that have complete sufficient statistics. And once that happens, a lot of interesting things happen. So any questions about the definition for this slide?
So complete statistics have to be sufficient.
No. A complete sufficient statistic is minimal. We'll see. Minimal sufficient. So completeness itself doesn't have anything to do with sufficiency. If it's complete and sufficient, so sufficiency is established elsewhere, and you also establish it's complete, then you have to be minimal sufficient. So that's going to be this tier. A complete sufficient statistic is minimal sufficient. Okay, that's what we'll prove. Complete.
It doesn't hold that.
No, we showed that there is a minimal sufficient statistic which is not complete. That's what we showed here. So in the Laplace family, the order statistic is minimal sufficient, as we showed before. And there's like a non-trivial function. So take, for example, the first element minus the second element. That's ancillary. Because it's ancillary, it's also first order ancillary, so it violates the definition. Yeah.
So to be complete, it should not be ancillary, right?
To be complete, it shouldn't be ancillary. Yes, it can be ancillary because then
It can be ancillary.
it can't be.
It can, so isn't definition for implying that is ancillary? Shouldn't be.
No. This is saying if it is ancillary, then f has to be constant. So it's a conditional statement.
Oh, okay.
So you pick any function f. If it turns out that f of t is ancillary, first order ancillary, then it has to be constant. It's like a conditional statement. Right, and sorry?
Interesting way of defining it.
Yeah, it's like a technical condition. It's really like a math condition. So you have to be good at math to not trip over this definition. It's like basically saying it can't happen. So no interesting function can be ancillary, but that's the way that they do it, right? It's not a straightforward definition. The straightforward statement is like this: pick a non-constant function, it can't be. But instead of saying it, they write it like this, which is a formal way of. So, but what you said is true. So an ancillary statistic can't be complete. Why? Because the identity function, so f of x equal x is non-trivial, and if I apply it to an ancillary statistic, it's going to be ancillary. So this is not. So that's true. Yeah, well, we're gonna have fun with this definition. It's not so obvious, but sort of clear. Right. The way it's set up is to help you to prove it. So you're gonna assume this. Right. It's the way that they set it up. So you're gonna assume and try to show that f is constant. Once you do it, then it's complete. So you assume start with the assumption, prove this side.
Sorry, I know we're hopping around a lot, but, so that function above in the example you wrote out for the order statistic,
Yes,
like x1 minus x2,
yes,
so that's a non-constant function, right?
yes.
And then it's ancillary because it's,
When you apply it to this, it's ancillary.
okay,
Yes, because the distribution of this quantity is independent of theta. Right. So we have a non-constant function, and you apply it to the statistic of interest, produces a statistic which is ancillary. Right. So this original thing cannot be complete.
okay, and then, but it's not, is it first order ancillary?
In this case, because the result is ancillary, then you apply that function. It's also going to be first order ancillary,
Okay,
right? This is not ancillary itself, right? The result of the function is ancillary and also first order ancillary.
okay,
Right. The statistic itself is not ancillary. It's minimal sufficient. It's a good statistic, but there are functions of it that are ancillary, and hence first order ancillary.
okay.
Sounds good.
And so because there are these functions, it can't be.
Because there are, yes, because we showed demonstrate at least one such non-constant function, this can't be complete.
Okay.
Yes. Perfect. Any other questions? Okay. So let's see, this is the example that I get. So let's see what we can do here. Okay, we can prove completeness, for example. In general, it's not an easy thing to show. It is, as you'll see, it's like equivalent to solving like a differential identity or integral equation. And showing that the solution is sort of for example, 0. But you're going to have some strategy. So there's a general result in exponential families, which we're going to talk about, although we're not going to prove the result, but we'll see exponential families after this. And in a certain class of exponential families, in the full rank exponential families, the sufficient statistic is complete. So that gives you a general class of these statistics. In other cases, there are some strategies. So let's do an example, see one strategy. So in this, one of the running examples is this uniform 0 to theta family, right? So 0 to theta. Okay, 1 over theta here. So this is a like a problematic family, if you remember, for a particular reason, right? The support sort of depends on theta, so it's not like a DCS family as we discussed. Nevertheless, it's an easy family to deal with because you can write everything down. For example, I forgot if we proved, I think we proved that, yeah, I think we proved that this is sufficient. The maximum using factorization theorem, we proved that it's sufficient. Now we're going to prove that it's complete. And then by the theorem that comes next, it's also going to be minimal sufficient. So the way to do it is, I'm going to set up this equation and then try to show that f has to be complete. So if this holds, then, sorry, f has to be constant. And for me to be able to evaluate this expectation, I need the distribution of t. And the distribution of t is sort of easy to calculate. So there is, this is the CDF of t. So so how do we actually calculate the CDF of t? See if anyone. Yeah, okay, so let's say this is the CDF. So this is equal, if the maximum is less than or equal to t, it means that all of them have to be for all I from 1 to n. And the xi's are independent, right? So this factorizes into product I from 1 to n, xi less than or equal to t, and so the CDF of the uniform is sort of easy to a certain extent. They just integrate that, it's just going to be a line. So it's like t over theta, I believe. And then you put an indicator as well, if t is in 0 to theta. Okay, and then you multiply, because all of the terms are the same, you get t over theta to the end. And then t has to be in 0 to theta. So it's fairly easy to calculate the CDF. And once you have the CDF, you can get the PDF. Right? How do we get the PDF from the CDF? Take derivative. So that's the derivative. So you take the derivative of this, you get n times, I'm putting the theta out. So 1 over theta to the n. So that's this part. And then t to the n minus 1. So all sort of good up to this point. Then I can calculate, so what I'm going to do is that I'm going to pick a generic function, which I'm going to specify. And I assume that this is equal to 0 for all things. So if you write them down, that would be an integral equation. So this is, so I want to set, like, pick a generic f and assume that expectation of f of t, basically of x, if you want, okay, just do t, it's easier. This is equal to c for a constant, and without loss of generality, you can take that constant to be actually 0. It's enough to show that if this is true, then f of t is 0 for like almost every t. Anyone can maybe argue why 0 is enough? that C here is, you can just set it equal to 0, for example, or any other constant if you want. Right? Anyone can say why that is fine? The thing is, this F is very general. Right, very much.
Like, shit.
Yes, you can basically, if I establish it with 0, then I'm applying to F plus C or F minus C, and then I get this. So if it holds for with 0, I can apply to a shift recursion of my function. And so just think about that. So because of the generality of F, I can just absorb C into that. And so for simplicity, we're going to do that. So I'm going to assume this part. So this can be written as an integral, right? So you can write it as integral f of t p t of t dt 0 to infinity, or like infinity, minus infinity to infinity. And this turns out to be integral 0 to theta, because that's the domain. That PDF is like n over theta to the n. That's this part. And then t n minus 1 dt. So we set this equal to 0. So this is saying 1 over theta to the n integral, or n, f of t tn minus 1 dt is equal to 0. This is for all theta bigger than 0. Basically. That's the parameter space. And so if it holds for all theta bigger than 0, I can just discard this part. Right? So this is going to be 0 is equal to integral 0 to theta f of t tn minus 1 dt for all theta bigger than 0. So this is some sort of an integral equation. So it's saying that this integral of f is equal to 0, and we want to solve this, basically find f. And the idea is that the only solution of this is 0. Obviously, the 0 function is a solution. But what we want to say is that this implies that f of t is 0. So anyone? Yes.
Doesn't this approach only support when the support is positive?
The support of what?
P,
Um,
because you could have a symmetric function, right? I mean, you can have something sum to 0 that's a sum of plus minus 1, but here, since everything is positive, it has to be.
so the thing is, it's not saying that this is 0 for a particular value of theta. This holds for any theta. That's a lot of constraints. Yes, it could have, like, suppose this was a symmetric function, right?
Yeah.
And yes, there are certain functions that you can put, and then this would be 0. But the idea is that this depends on theta. So I should say, like, if you want. And this is saying that it's not for just that particular theta, it's just all for anything. Okay. And this is a lot of constraints and forces. It's not positive negative. Positive or negative. It's just the amount of information that this like imposes, the amount of constraint that imposes on F, in some cases is enough for it to be used. Because it has to integrate against all of these. One of them could be symmetric, but not necessarily all of them. Or like there's this variance could be different or something like that. It's an interesting point to note, but positivity is not key here, right? For example, I could probably do minus theta and theta, and it should be fine. This is max is not going to be minimal sufficient, but let's we could do like -1, something like that. So that's also not positive. This should be fine as well. for the other one, there's something else which is minimal. So, um, okay, so back to this. Why this implies?
Can you take derivative from?
Yes, yes, that's a good strategy. So what happens if we take derivative? A very fundamental. So let's first to take the derivative. So this side is 0. What is the derivative of the other side? F of theta, theta n minus 1. Why? The what? Fundamental theorem of calculus, yeah. So the fundamental theorem of calculus tells you that the integral of, if I define a function, it's integral of like g of t dt. And there's a theta here. This is differential with respect to theta, and the derivative is just g theta. So assuming like for all theta, fundamental theorem of calculus. If you see, if you want, this holds for all theta, positive, so I can like cancel theta. Okay. This is implies, and this is equivalent to f theta being 0 for all theta. This is actually for almost all theta. Because that is almost everywhere. It's not at every point necessarily, because I can redefine theta at a single point, and it doesn't. So I redefine g at a certain point. So if you want to be careful, its differential and derivative is almost everywhere equal to g theta, and so you can say that this is for almost every theta for almost every theta. And that's good enough for us. Should be almost everywhere, let's say, relative to some underlying measure against which we have the density. In this case, Lebesgue. So it proves sufficiency. You can see it's like a conditional statement. We didn't specify f. At the start, pick a general f, solve this integral equation or differential equation, and it turns out to be 0. So basically, you have to show that the only solution of a differential or integral equation is 0. Sounds good? Right, so that's one strategy. Sort of based on definition.
For the CDF P. Why did you plus
Oh, right. Yeah, so the CDF is not, so this is, this wasn't what I wrote here is not correct. This is correct. So this holds for theta in 0 to theta, but the CDF just, it doesn't go back to 0 once you hit 1, it stays at 1, right? So technically I have to put that there. So it's going to be like, goes down, like goes up, but once you hit 1, then it stays at 1. When we take the derivative, it's going to be 0 here and there, right? Sounds good. So P is complete, T is sufficient, and we'll see that T is going to be minimal sufficient as well. But this is better than minimal sufficiency. So sort of what this is saying is that whatever non-trivial function you apply to this max, it contains some information about theta. You can make the distribution lose information about the theta, which is a pretty strong sort of problem. Questions? So if there's no questions, we can take a detour. I want to prove a result, like the minimal sufficiency follows from sufficient complete. If you have a sufficient complete statistic, then it's minimal sufficient. But we'll need a property of conditional expectation, which turns out to be very useful in its own right. So I'm gonna take a detour and talk about conditional expectation as L2 projection. Okay, and then we'll come back. So this idea is a geometric way of looking at conditional expectation. So hopefully everyone knows conditional expectation. You've been dealing with things like that. This lets you view it as a projection of it. So the way to do it is that we can look at the space of random variables that have finite second moment. So x's for which the expectation of x squared is finite. This is called the L2 space of the probability space. And then we can define an inner product on this space. So this is going to be a linear space in the sense that if I add two random variables that are in the space, it's going to be in the space. If I rescale a random variable in the space, it's going to be in the space. And once you have a linear space, it's a little more than a linear space that also has like nice completeness properties in the sense of analysis. Sort of, it's like okay, let's not mention that. We need an inner product. So you can put an inner product in the space. And if you look up Wikipedia or you've seen this before, there is an abstract definition of inner product. So it's like a bilinear form. Bilinear means it's linear in either of the arguments, which has certain properties. So for example, x has to be positive or non-negative, and x 0 implies that x is 0, something like that. And also bilinearity. That means that like alpha x plus beta y. Z is alpha x z plus beta y z. So a bunch of properties, the usual properties of inner product in Euclidean space. If you remember, the natural ones sort of are abstracted away and used as a definition of the product. So if I define the inner product of two random variables in L2 as the expectation of the product, then it satisfies all those properties. So it's a valid inner product. Once you put this inner product on the space, this is an inner product linear space, and it turns out to be like complete in the sense of analysis. So it's what they call Hilbert space. Cauchy sequence converge and so on. So we don't worry too much about this. But it also gives us a norm. So any inner product gives you a norm. Once you evaluate the inner product of x itself and take the square root, that defines a norm. Okay. Yes. Yeah. So these are real. Everything is real. There's no complex numbers. Yeah. So you can like think of complex. So all linear spaces for us are real linear spaces. So these are. Conjugate, you mean complex conjugate? Yeah, so everything is linear. You don't worry about complex.
If we know.
Not linear, real. Yes, go ahead.
So if we know expectation of x squared is 5 and x y squared.
Yes.
We know for sure expectation of x
Um,
we know like the inner product is.
yes, you know that the inner product is well defined. How do you know that? It's a good question. So if I know that expectation x squared is finite and expectation y squared is finite, is this well defined? Okay, so you can actually show that the expectation of x squared finite, expectation of y squared finite implies that the expectation of actually the absolute value xy, because this is in general well defined, but can be infinity. This is going to be also finite. Once it's finite, then that makes sense. So why is that? Sorry. Yes, okay, so that's the Cauchy-Schwarz inequality, okay. So, Cauchy-Schwarz applied functional form of Cauchy-Schwarz. So remember the random variables are sort of functions and the probability space. So this is really, yeah, do we want to go there or not? But this is the Cauchy-Schwarz. So this is saying xy is less than expectation of x squared, like root, and then root expectation of y squared. Cauchy-Schwarz for functions. Shall we go there? Or not? So these are like integrals. So this is integral x omega y omega dp omega. And these are integrals. So imagine this is the integral. So the Cauchy-Schwarz that you learn, like maybe first is for discrete, but like let's say AI, BI. Either absolute value here or inside, you can put it inside. It's less than AI squared root BI squared. Okay, so if you replace the sums with integrals, then that's the Cauchy-Schwarz, the functional form. And it's true. And so this implies that once these two are finite, then it's finite. And so this is the inner product is well defined. That's what we actually, why we actually deal with the L2. Great question. But it's a detour on the detour. So let's not go there. And so the point is, now I have a norm. And then the norm means is a distance. I can look at the distances of random variables. So I can say x minus y of the norm. Okay, so you can think of this geometrically, the inner product is related to the angle and norms, and so the distance also relate. So think of this as just usual Euclidean objects. Okay, so think of these as vectors. This is an inner product. The Cauchy-Schwarz really defines it. So if you divide this by this side, defines some sort of an angle, cosine of an angle. And then we can also have the length and the distance. And so this distance would be, if I look at the square of it, it's just the expectation of x minus y squared, right? So just apply this definition. And you can call it the MSE, mean squared error. So the distance of two random variables is the expectation of the difference squared or mean squared error. And I can define orthogonality. I can say x is orthogonal to y equal to 0, or expectation of x times y is 0, and so on. Okay, we have distances, we have orthogonality, we have this, like, yeah, norm and stuff. Then I can also start defining projections. Once I have a distance, I can say, okay, what is, for example, the closest x with these set of properties to y? So if I impose some constraints on the class of x, within that class, what is the closest random variable to y? And so that's what I'm going to do. I'm going to define this class of functions that, sorry, the class of random variables that are functions of x. Okay, so pick x, both x and y are M2. Look at all the functions g of x. This is a new random variable for any g. Let's say the expectation of g squared is also finite. So g of x is in L2. So these are all random variables in L2 that can be written as a function of x. Right? And like measurable, to be precise. And so this space, it turns out to be a linear subspace of L2, because if I have like G1 of x in this space, and then I have G2 of x, then G1 plus G2 is another function of x, which is also in the space. And if I rescale it, it's going to be the case. So it's like a linear subspace. Imagine just there is a linear subspace of L2, which is this L, containing all possible functions of x. And then I have particular y, which may not be a function of x outside here. Because it's a linear space, I can project it. I can get the closest in this L. Let's call this y hat. The closer element in L to y in the distance that I define. Okay? So we minimize y minus z, where z varies in this L. So this is definition of projection. And the argument, we call it y hat. So this exists if the subspace is linear and closed, which is true. And so there is a unique L2 projection in the sense that among these, you think of, let's say there is some origin here. I'm going to write these as vectors. Among all possible vectors here, there is one that minimizes the difference, y minus y hat. So basically, y minus y hat is less than or equal to y minus z for any z in L. So the existence of something like this follows from the general theory of Hilbert spaces, let's say, which L2 is one. So this projection we call the conditional expectation of y given x. And this is like an abstract way of defining conditional expectation. So it's so by definition, it's in this class. So this turns out to be some function of x. Let's call this g hat, and that particular function of x is the conditional expectation of y given x by definition. Because we define conditional expectation of y given x to be g hat of x. A couple of things like that follow is that first it's a function of x, and it's also the closest function of x to y in L2. And so I can say, for example, y minus expectation of y given x. This is by definition that g hat x is less than or equal to expectation of y minus g of x for any g such that this is g of x is in L2. Okay, so this distance is minimized. Okay, because the projection exists, I can define it like that. Okay, then a lot of like intuitive like properties follow. For example, I know that this in L2 space, or like the inner product space, the Hilbert space, the difference has to be orthogonal to L. That's another like intuitive idea. Once you find the solution of this, the solution is characterized by the difference being orthogonal to L. So I would know that this g hat of x is orthogonal, or sorry, the difference y minus g hat of x is orthogonal to g of x for any g of x in L2. And so this orthogonality is the source of a lot of information. Okay, one example is it's orthogonal to constant functions because g of x being a constant is in L2. So I can take this, for example, to be a constant function, y minus g hat of x is orthogonal to 1, the constant function. And this is equivalent to expectation of y minus g of x times 1 is 0. That's the definition of orthogonality. And so this is expectation of y is equal to expectation of g hat x, which is by definition expectation of y given x. Right, so this is saying expectation of y of x is expectation of y. Okay, so this should look familiar. It's like the smoothing property of conditional expectation. So if I take the expectation of this guy is equal to expectation of y, what it's really saying is the projection error is orthogonal to constant functions, but it's also orthogonal to a lot of other identities like this. But this we get for free, for example. So we are out of time. So we'll come back next time. If you have questions, let me know. But think about this if it was not clear. We'll come back, but this view is very helpful. Conditional expectation is the best prediction of y based on functions of x. This prediction means closest in the MSE. Okay, so that optimization view or geometric view of conditional expectation tells you a lot more. So for example, if we want to estimate y given a function of x, and your loss is L2, then this is the best you can do. Okay. So from a statistical perspective, it's useful. So the best thing you can do under certain loss is this. So this is gonna be something that we're gonna work with a lot. Sounds good? Okay. Thank you guys. See you next time. Rob.